Okay, hi everybody. So, what is the definition of absolute convergence? Okay, so a series, the sum of the Cn, where each Cn may be complex, so it could be a series of complex numbers or real, is called, so a series is called absolutely convergent when, okay, now here's the definition. A series is called absolutely convergent when the associated series of absolute values, so just take the size of each complex number or each real number or whatever, take the absolute value and add that and sum that. The associated series of the absolute values converges. Okay, so some series is absolutely convergent when this other series converges. Okay. Prove that absolute convergence implies convergence. Okay, so assume that the sum of the absolute values of the Cn converges. Now, we need to show that the sum of just the complex numbers themselves as a series also converges. Okay, that's what we need to prove. That, if we prove that, then we've shown that absolute convergence implies convergence. Okay? Because notice, we didn't say whether this series converged or not. We just said some series, adding up complex numbers, is called absolutely convergent when this series converges. Now what I want to prove is that if this series converges, then also this one converges. Super useful. Okay. Okay, so to show that, we will show the sequence of partial sums converges. And actually, if we show it's Cauchy, then it automatically converges by a previous result. Cauchy sequences converge. So we're going to look at this infinite sum, and we're going to show it converges by looking at the sequence of partial sums. Okay, well that's sort of obvious. That's the definition of convergence. You have to look at the partial sums. So we're going to use the definition of convergence, and in particular, we're going to show that the sequence of partial sums is Cauchy. Okay. Do you remember what Cauchy is? Well, anyway, let's look at the sequence of partial sums. Let's say that S sub m is C1 plus ... all the way up to Cm. Okay, that's the partial sums. And to be Cauchy, a sequence is Cauchy if, and let's just remember this, for all d, there exists an n such that any pair past n implies that this is less than d. Okay, this is sort of in our minds. This was the definition of Cauchy. Yeah. Okay, so now look at this subtraction. Note that Sm minus Sn is equal to, well, add up the first m terms and then subtract the first n terms. You'll be left with Cn plus 1 plus Cn plus 2 plus all the way up to Cm minus 1 plus Cm. Okay? So that's what happens. Think about that. You have all m terms here, and you're going to subtract away the first n of them. Here I'm assuming m is bigger than n, but whatever. You could just call them different names, whichever one is bigger. Okay. But now, look at this. We have absolute value of a sum But by the triangle inequality, this is less than or equal to the sum of the absolute values all the way up to the nth term. C, yeah. Okay. And now here's my claim. This will be less than D. Okay, so but let's set it up properly. So to show Cauchy, we need to show like, okay, so let some positive D be given. Okay? We need to show that there exists an index such that all pairs have this less than D, which is right here. And so we'd like to show that this is less than D, and we would be done. Since this sum converges, since the sum of absolute values converges, look at absolute values, its sequence of partial sums is Cauchy, because its sequence of partial sums converges, and hence any convergent sequence is also Cauchy. And so we proved that before. Its sequence of partial sums is Cauchy. Thus, there exists a capital N such that m and n past that point implies, and now these partial sums, so let's call them Tm minus Tn is less than D, where, okay, what's Tm? Where Tm is equal to C1 plus C2, and they're the partial sums of this absolute value sequence all the way up to Cm, and Tn is just the same ones, except maybe up to a shorter. Okay, and now if we subtract them, what do we get? If we subtract these two, we get exactly this. Do you see that? So that's exactly what we needed. But then Sm minus Sn is, less than D by star. And here's my, this is a previous calculation I did. Okay, so that means they're Cauchy. We've showed that for any D, there exists an N such that this pair, for any pair bigger than N, this thing is less than D. Right there. Okay. By star, maybe just to be clear to the reader, like, because I'm talking to you, but I didn't write it, by star, and since Tm minus Tn is this. Okay, so that's good. So now your book doesn't prove it this way. I like it this way because to me this is intuitive. If Cauchy sequences are sequences where if you go out far enough, all the terms are really close to each other. They're zooming in on something. They're gonna converge. So to me, if somebody wants me to prove that a certain sequence is convergent, to prove it's Cauchy is intuitive. Now, our book proves it a different way. I think because, it's basically like this, all these tricks, like special case where it's real, and then you get this inequality, which is totally like, why are we doing this? And then you have to go to this. I don't know. You can read our book's proof. And it finishes, and this is totally like tricky. I just think that the book is probably proving it this way because it works. It's a trick that works, and it doesn't require Cauchy, and it made the Cauchy section 2.8 optional, but we covered the Cauchy sequences, and so why not use them? And now we have a proof that's sort of, in my mind, straightforward and intuitive and does not require any tricks. It requires the triangle inequality and knowledge of the definition of Cauchy sequences. Okay, and so I like this proof a little better.